Hello everyone, I am Bilvesh K. In this video, I am going to explain about two-dimensional continuous Fourier transform pair, both in polar coordinates and also in rectangular coordinates. And also we will be discussing about 2D impulse function and its shifting property. Let us discuss about the one-dimensional impulse function. Generally the impulse function is a very important elementary signal which is used in which has very dynamic uses, and it is theoretically it is nothing but a very short pulse. Generally the impulse function is a pulse that is much shorter than the time response of any system. An ideal impulse signal is a signal that is zero everywhere except at the origin. At the zero it is infinitely high. And also let us discuss about the continuous impulse one-dimensional impulse function. For suppose it is denoted by a symbol del of t, where t is a continuous variable. Del of t is equal to infinity at the t equal to 0, and for t is not equal to 0, it is 0. So, and also if we find the summation minus infinity to infinity del of t dt, that will be equal to 1. As we see in the figure, it describes about a discrete unit impulse signal at the point x0. The signal only lies at the point x0, and remaining all the signal will be 0. At point x0 the signal will be 1. Similarly, we can extend our definition of the one-dimensional impulse function to define the two-dimensional impulse function. It is also infinitely high and infinitely narrow pulse with the area of unity. So, for suppose if you want to define a continuous two-dimensional impulse function, we have to consider two continuous variables. For example, t and z. So, it is defined as del of t comma z is equal to infinity if t equal to z equal to 0 and 0 if otherwise. So as we see, the summation x as t tends to minus infinity to infinity and z tends to minus infinity to infinity, del of t comma z dt dz will be unity. So similarly we can define the discrete unit impulse also. Here it also serves the same purpose of the continuous impulse function, but here the x and y will be in discrete. So del of x comma y is equal to 1 if x equal to y equal to 0, and 0 in other cases. In the figure we can see a discrete unit impulse function located at x0 at units x0 comma y0. Del of x minus x0 comma y minus y0 will be 1 only at the point when x equal to x0 and y equal to y0. We can plot a two-dimensional discrete impulse function in the MATLAB. As we see, we can take two variables xd and yd. Both will be ranging from minus 10 to 10 with the step of 1 unit. And then we can consider a signal in which initially we will be having zeros in all the directions, in the x direction and also in the y direction. And then we will be locating the signal to be value 1 only at x equal to 0 and y equal to 0. And by using this stem function we can plot the impulse function. Then we can observe that in the given figure every point will be 0 and only the signal exists at x equal to 0 and y equal to 0. This will be our 2D discrete unit impulse function. By executing the following code in MATLAB we can observe the following 2D impulse function. Let us discuss about the shifting property of the impulse function. So suppose the integral of a impulse is 1. So if we consider the integral a to b del of t dt is equal to 1 in the range of when a less than 0 less than b and 0 otherwise. So in other words, if the integral includes the 0 where the impulse lies, the integral is 1. So if it does not include the origin, the integral is 0. Likewise, similarly, if the impulse is not at the origin, integral a to b del of t minus lambda dt, that will be 1 when a less than lambda less than b and 0 otherwise. So for suppose if you want to evaluate integral minus infinity to infinity del of t into f of t dt, we can simplify this integral by noting that because the impulse is 0 everywhere except when t is equal to 0, so we can simply replace del of t into f of t by del of t into f of 0. As we know, the impulse only exists at the 0 value only. So It means we can replace the product of two functions, which is very typically difficult to integrate, and replace it by the product of a function and a constant, which is easy to integrate. So we continue the deviation by pulling f of 0 out of the integral. So integral minus infinity to infinity del of t f of t dt will be simply nothing but f of 0. So generally from these can be similarly applied to the two dimensional function also. When integral x t tends to minus infinity to infinity and z tends to minus infinity to infinity, f of t comma z into del of t comma z dt dz will be simply f of 0 comma 0. So this is called the shifting property because the impulse function del of t minus lambda shifts through the function f of t and pulls out the f of lambda. So said like similarly, we can simply define it as we can replace the value of t in the function f of t by the value of t that makes the argument of the impulse equal to 0. In general case, it will be like lambda, some t equal to lambda. Let us discuss about the Fourier transform pair. Firstly, we will discuss about the one-dimensional Fourier transform, and then we will be introducing about the two-dimensional Fourier transform in rectangular and polar coordinates. So, if you see, the main need of introduction of Fourier transform is the drawback of Fourier series, as it is only applicable to periodic signals. It is not applicable to aperiodic or non-periodic signals. As we see, every signal can be the Fourier series suggests that every signal can be represented as a sum of sines and cosines. So, if we see if a signal is not periodic or aperiodic signal, then we cannot represent it in the form of Fourier series. So, this drawback is overcome by the scientist Fourier and developed a mathematical model to transform signals between time domain to frequency domain. So which is nothing but the Fourier transform. The Fourier transform is nothing but the generalization of the complex Fourier series in which the limit is extended to infinity. So as you see, the Fourier transform of a continuous function f of t of a continuous where t is a continuous variable is defined by capital F of nu is equal to minus infinity integral minus infinity to infinity f of t e power minus j 2 pi nu t dt, where nu is the frequency, where f of nu, the obtained domain will be called as frequency domain. And similarly, if we have given the function in the frequency domain, we can obtain it back in time domain by using the inverse Fourier transform, which can be written as f of t is equal to integral minus infinity to infinity capital F of nu e power j 2 pi nu t d nu. These above two equations from which one can be derived from another is known as Fourier transform pair. The both equations like Fourier transform and inverse Fourier transform are called as Fourier transform pair. Now let us define the two-dimensional Fourier transform pair in rectangular coordinates. Let us consider the signal f of t comma z to be a continuous function and it contains of two continuous variables t and z. The two-dimensional continuous Fourier transform for this function can be defined as capital F of nu comma v, where that is equal to integral t tends to minus infinity to infinity and integral z tends to minus infinity to infinity f of t comma z e power minus j 2 pi into nu t plus vz into dt and dz, where here the new variables nu and v are the frequency variables. While when we are referring to the images, t and z are interpreted to be continuous spatial variables, as similarly in the case of one-dimensional case, the domain of the variables nu and v defines the continuous frequency domain. Similarly, we can also define the inverse Fourier transform, from which if we are given capital F of nu comma v, we can obtain back the small f of t comma z. Small f of t comma z is equal to integral nu is equal to minus infinity to infinity and integral v is equal to minus infinity to infinity capital F of nu comma v e power j 2 pi into nu t plus vz into d nu into dv. So Fourier transform is nothing but it is an expansion of f of t comma z multiplied by sinusoidal terms whose frequencies are determined by the values of the variable t and z is integrated out as mentioned earlier. Because the only variable left after the integration is frequency, so we can say that the domain of the Fourier transform is frequency domain. That's Find the two-dimensional Fourier transform in polar coordinates. If any function given in rectangular coordinates, we can introduce the polar coordinate by simply substituting them as x is equal to r cos theta, y equal to r sin theta, where r is the radial distance and theta is the angle. Similarly, in the spatial frequency domain, we can similarly substitute that omega x, suffix x equal to rho cos phi and omega y equal to rho sin phi. It then follows that the following 2D Fourier transform can be written as f of psi rho comma psi, that is equal to integral r tends to 0 to infinity and theta tends to minus pi to pi f of r comma theta e power minus r rho cos of psi comma theta r dr d theta. This gives the polar coordinate Fourier transform equation. By applying this, we can find the Fourier transform in polar coordinates, where psi, rho, and psi are the frequency domain variables, and r and theta are the time domain variables, where r is the radial distance and theta is the angle. And similarly, we can find the inverse Fourier transform also can be written as f of r comma theta is equal to integral 0 to infinity and integral minus pi to 2 pi capital F of rho comma psi e power I r rho cos of psi minus theta d psi rho d rho. Here r square is equal to x square plus y square, and also theta can be given as the arc length of tan of y by z. And also similarly these can be converted in the spatial domain applicable also. So rho square is equal to omega x square plus omega y square, and psi equal to tan of omega x by omega y. Let us solve a problem on Fourier transform. We will be considered. Let us see the image given in the following slide, and we will be finding the Fourier transform of the given two-dimensional function. Let us consider the Fourier transform equation in two dimension. Capital F of nu comma mu is equal to t tends to minus infinity to infinity and z tends to minus infinity to infinity. F of t comma z e power minus j 2 pi into nu t plus vz into dt and dz. As we see, the f of t comma z is nothing but the value a. So the limits will be reconsidered as minus t by t tends to minus t by 2 and z tends to minus z by 2 to z by 2. A into e power minus j 2 pi into nu t plus vz into dt and dz. So simply we will be getting, by solving this, we will be getting the Fourier transform as a into t into z into sinc function of pi nu t and sinc function of pi mu z. So as we see, if we find the spectrum of this function, we'll be seeing this as following image. So in the image we can see that the larger the t and z values, the more contracted the spectrum will be, and similarly the vice versa also takes place. As we see, the block is longer in along the t-axis, so the spectrum is more contracted along the u-axis in the frequency domain. So if the spectrum is longer in time domain, then it will be more contracted in the frequency domain. If the box is small in the time domain, then it will be less contracted in the frequency domain. So we can conclude this from the following example. Discuss about the conditions for the existence of Fourier transform. Any function f of t can be represented by using Fourier transform only if it follows the Dirichlet's conditions. The Dirichlet's conditions are: the function f of t should have a finite number of maximums and minimums, and also there must be a finite number of discontinuities in the signal f of t in a particular interval of time, and it also should be absolutely integrable in the given interval of time. That is nothing but some in the given interval of time, the value should be finite value. The integrated value should be finite value. So that's all about the two-dimensional Fourier transform and the impulse function and its shifting property. If you have any doubts or any queries, please post in the below comment section, and do not forget to subscribe the DSP and IT channel. Thank you.